part 2 of the video about imaging and ray diagrams. This time we're going to talk about imaging equations. So in the last video we talked about how to draw ray diagrams to lenses and mirrors and what images do we see, are they virtual or real, magnified, etc. This time we're going to actually calculate them to kind of check our work. We can calculate magnification, and we can also use these equations to kind of check our ray diagrams to make sure that they are correct and get more detailed information about it. So this video is going to also kind of review what we did in the last video about how to draw the ray diagrams, but also now how to calculate things about them. So let's go over our 4 equations we're going to talk about. First equation is 1 over f is equal to 1 over v plus 1 over u. So what do those things mean? So f stands for the focal length. It's a length from the center of the lens of the mirror to where it focuses, that focal length. And it's usually measured in meters, but it can also be measured in centimeters, is a common one too. V, don't be confused with final velocity or initial velocity for v and u. It's kind of confusing. This is a separate topic, keep it separate. So v, in this case, is the image distance. How far away is the image from the lens or mirror? That distance in centimeters or meters. And the object distance is u. How far away is the object from the lens? Like this arrow to the lens. So image distance, object distance, and focal length distance. The next equation is magnification. These are both linear magnifications. Like how many times larger is the image? If m equals 1, m stands for magnification. If m equals 1, then it's exactly the same size and it's the same direction. If m is negative 1, that means it's the same size and flipped upside down. So negative numbers means that they're flipped upside down. Positive numbers means it's the same size. So there's 2 equations for that. The first one's pretty obvious. The magnification is equal to the height of the image divided by the height of the object. So if the image is 2 centimeters tall and the object is 1 centimeter tall, it's 2 over 1, which is twice as big. Makes sense. If the image is negative 2 centimeters, like 2 centimeters below the principal axis, and the object was 1 centimeter, that's negative 2. It's twice as big and flipped upside down. We can also calculate it with negative v over u. So the negative image distance divided by the object distance. The last equation we're going to talk about is angular magnification. So sometimes you don't want to worry about how much bigger it is, but how much bigger is the angle. So here's an example. When this object goes through a lens, it produces an image on our sides, flipped upside down, and we can make a triangle with it from the principal axis up to the tip of the arrow. And that angle right there, measured in either degrees or radians, would be the object angle. And then if I want to find the angular magnification, which is labeled by a capital M, not a lowercase m, capital M is angular, it's the object angle over the image angle. In this case, it's probably going to be 1, based on the way I drew it. So what we're going to do now is we're going to go over some example problems. So I'm going to go through a couple of different example problems, draw the ray diagram, use these equations to kind of calculate these things, and kind of verify array diagrams and calculate magnification. Okay, let's try an example problem. Our first example problem we're going to do is with a concave mirror. So remember, a concave mirror is one that curves inward. So let's say this is the back of the mirror, this is the front of the mirror. So a lot of times IB likes to just draw something like this. Instead of drawing the mirror like this, where it's curved, they just draw it with a line. Saying this mirror is big enough that the light's going to hit it, it doesn't extend past the mirror. So they just draw it with arrows. This is my object, labeled as O, and this is my mirror, labeled as M. And our F is labeled as the focal length, or the focal point. So what we're going to do for this, we got some data here. So the height of this object is 2 centimeters. The focal length is 25 centimeters. The distance from here to here is 50 centimeters. I kind of approximated these. We're going to calculate the image distance. We're going to calculate the magnification. We're going to calculate the height of the image. And then we're going to draw a ray diagram and see if it actually matches up with our calculations. So let's go over the first one, calculate V. Well, the way to calculate V is what we know. We know F and we know U, so we can plug it into the equation. So 1 over F, which is 0.25, but Since all of these are just ratios, we can just actually leave them as centimeters. So I'm too lazy to convert it. It's 0.25, but 1 over 25 is equal to 1 over v, which is our unknown, plus 1 over 50. All right, so solving for v. Let's see here. 1 over 25 is 0.04. 0.04 equals 1 over v plus 1 over 50, which is 0.02. I can subtract 0.02 from both sides. So 0.02 is equal to 1 over v. Multiply both sides by v, and then divide by 0.02. 1 divided by 0.02 is 50. So what's my v? It's 50 centimeters. Okay, so let's go to m. Let's calculate m. So looking at magnification, our magnification is equal to negative v over u. So m is negative v, which is negative 50, over 50, which results in a value of negative 1. There's no units. We're taking centimeters divided by centimeters. It's negative 1, which means that it should be the same size, but negative means it's upside down. Let's calculate the height of the image then. Using, now that we have the magnification, we can use the other one to find the height of the image. So negative 1 is my m. The height of the image is my unknown. The height of the object is 2 centimeters. So I can multiply both sides by 2. The height of the image ends up being negative 2 centimeters. All right, now I'm going to erase the math here to get some space. Let's see what our ray diagram actually looks like and see if it matches up with what we thought it should be. So remember, for a concave mirror, we can draw 2 rays. First ray is parallel to focal point. So I can draw my first ray is parallel to the principal axis, and then bouncing back to the focal point. The second one is to the focal point, bounce back to parallel. Look at that. They cross right there below the principal axis. So as my tip of the arrow here, not lined up perfectly, pretty close. My arrow's like, well, it's close. So let's verify. What is my, if this is 50 from the object to the mirror, if the object distance is 50, this is pretty close. My lines aren't perfect. These distances are not perfect. I just kind of estimated it's 50. From here to here is also 50, so check. What's magnification? It's negative 1. Negative means it's upside down, and it's the same size. Okay. What's the height of the image? Well, if this is 2 centimeters, this is going to be negative 2 centimeters because it's below. Our ray diagram indeed matches what our calculations show. So you can use your calculations to kind of verify things and get more data about it. The ray diagrams is a good visual. So if you're a good drawer, the ray diagrams is another way to do it, to save yourself some math. Let's try another example. Okay, different data. Last time we tried a concave mirror. Now let's try a converging lens. So it's the same thing. So we have an object over here. It's 50 centimeters from the lens. Our focal point is 20 centimeters. So I kind of trying to draw the scale here from the lens. And the height of our object is 10 centimeters tall. And we're going to do the same thing. We calculate the image distance, calculate the magnification, calculate the height of the image, and draw the ray diagram to verify that these work. So remember with let's go through the equations first. So first equation, we have 1 over f, which is 1 over 20, is equal to 1 over v plus 1 over u, which is 1 over 50. So 1 over 20 is 0.05. This is 1 over v plus 1 over, I think we did it last time, 0.02. Subtract 0.02, no, not 1 over 0.02, my bad. 0.02, that makes more sense. Subtract 0.02 from both sides. You get 0.03 equals 1 over v. Kind of do a cross multiplication here, multiply by v, divide by 0.03. 1 divided by 0.03 is 33.3. So the image is 33.3 centimeters from the lens. Okay, let's look at magnification. Magnification is negative, I'm off the screen here, sorry, negative 33.3 divided by 50. So negative 33.3 divided by 50 is negative 0.666. No value on that. The devil made me do it. Sorry, that was a bad joke. So negative 0.666. All right. So 2/3 the height and upside down. And then calculate the height of the image. Well, we just showed that it's 2/3 the height. Well, we can use that equation right here. Negative 0.666 times 10. The bottom gives us negative 6.66 centimeters, which means it's upside down and a little bit smaller. Now, let's see what the ray diagrams look like for this lens here and see if it matches up. So remember, ray diagram for a converging lens. So the first ray goes parallel to the focal point, so through this focal point, and then it goes through this focal point to parallel. And it crosses right there, below the principal axis. Okay, this is where my ray diagram is not pretty. I can't draw straight lines apparently. But if we look at this data here, let's calculate V. So V says it's 33.3. Now, if I look at this distance here, even though I'm not a very good drawer, this is 50. Look at the distance on the other side. That is, like, this is 20. This is 50. It's somewhere between 20 and 50. It's 33.3. That's what it should be. I'm just not very good at drawing straight lines. Calculate the magnification of the image. Well, let's do the third one first. Calculate the height of the image. If this is 10, we know it's negative. Our height of the image is negative. So it's flipped upside down. This is 10. Yeah, it's a little bit bigger. So it's roughly 2/3 the size. So it's below the axis. Magnification is about 2/3, but flipped upside down. So there we have it. Okay, so concave mirrors and convex lenses are pretty easy. They're pretty straightforward, and they're very applicable for like imaging, like telescopes and microscopes use quite a bit. But there is one weird one. There's a weird one that happens with a diverging lens. Because remember, diverging lenses always make virtual image. So what happens if you have a virtual image? What happens to these equations? Nothing happens to the equations, but something does happen to the focal point. So this one, let's go through the same thing. This is not a converging lens, but a diverging lens. So remember, a diverging lens, I'm sorry, this is getting red, is one that is skinnier in the middle and thicker on the outside. So the rays actually spread out when they go through the lens. And so we're going to do this one in a different order. Let's start by drawing the ray diagram. What does that ray diagram look like? So ray diagram comes in, it's parallel, and then the focal point, instead of going this way, it actually goes up this way as if it were going through this focal point. That's one ray. I'll do the other one in red. This ray heads towards the other focal length, or focal point, and then it goes parallel. These never meet up on the other side of the lens, so we have to trace them back to get a virtual image that line is terrible. Yikes. They cross right about here. So the question is, like, does that break our equations? Like, how would we figure this out? How would I figure out what that image is using understanding equations? Well, so we have the ray diagram, so we know what it should end up being. Now let's go through the equations and find what happens. So here's our image height, 10 centimeters. Okay, same last time. Our image height, object height. The object distance is 20 centimeters. Now here's where it gets tricky. The focal point, the focal length, the focal point is 10 centimeters away from here, but we're not using that focal point, we're using this one. Because it's diverging. So the focal length is actually 10 centimeters on this side of the lens. So virtual images have negative focal points. So that's one thing to remember. If you create a virtual image, you have a negative focal point. And that happens for diverging lenses. And it also happens if you're really close to a converging lens. So negative focal points for diverging lenses and or just any virtual image, which happens with divergent lenses or magnifying glasses. So let's go through it. Let's go through it. Let's see what happens. Let's use the calculations here. See what we get. So using the first equation, we get 1 over f, which is 1 over negative 10, equals 1 over u, or 1 over v. We can also put 1 over u plus 1 over v. That doesn't change the math at all. Plus 1 over 20. Now, look into this math here. On this side, we got negative 0.1. Here we have 1 over v plus 0.05. Now I have to subtract 0.05 to the other side. So negative 0.1 minus 0.05 is negative 0.15 equals 1 over v. Now I can multiply by v and divide by negative 0.15. So I take 1 divided by negative 0.15, and I get v is negative 6.67. Negative. So that means that the image is 6 centimeters away, but not on that side. It also tells me if I get a negative image distance, I have a virtual image because it's on the opposite side of what I expected it to. Right, that's the positive side. This is negative. Calculate magnification. Okay, using that magnification equation, m equals negative 6.67 over, because it's a negative equation, but it's also a negative number, over whatever, 20. So we end up with a positive 6.67 divided by 20. We get 0.33. That tells us it's a positive magnification of 0.33. So this is roughly 1/3 the size. It's not drawn to scale. Obviously, you can see it's smaller though. Mine's about half the size. Okay, so if it's 1/3 the size, you basically calculate the height of the object or the height of the image. You multiply by 1/3, and you get 3.3 centimeters. So does our ray diagram match that? Yes, it does. The distances are all matched up. This is about 6 centimeters. If this is 20, this is about 1/3 of that for the distance, and the height's about 1/3, and it's upright. So we did get a positive magnification. Let's do one final one. One final one. What if we have multiple things? Now, my guess is you probably are not going to run into a lot of diverging lenses because they're not super applicable in a lot of imaging settings, unless you want to make something smaller. But let's go over an example of like a microscope, where you have multiple lenses working together. How do you calculate that? All right, let's apply one last example. What if we have like a microscope, which uses multiple lenses? What we do, it's simple actually. We just break it down into 2 steps. So let's say this is a converging lens and not a converging lens. What happens? So let's actually start by drawing the ray diagrams. Once you know it's like in a microscope, you can actually play around with these distances. And remember, if you play around with the distances, you can actually change the magnification and the focal length and stuff. Not the focal length, but the image distance and stuff. So let's show what the ray diagram looks like first. So parallel to focal point to parallel. So they cross right there. And that's, I'll do that in red. It's upside down. And there you go. Now this lens, we're going to say that it actually lines up with the same focal point, which is a much bigger focal point. So what we do is we take that image that was formed, and this lens, we treat it like the object. So now we just draw a ray diagram for this with respect to that. So we go parallel through the focal point. Oh, that line's terrible. And you get better at drawing straight lines here. It's better. And then through this focal point, and this is why they extend the arrows down so you don't run out of lens to hit. Through the focal point to parallel. Oh my gosh. So if you see, these lines will never meet up. So what we do is we trace them back. My lines are not going to be straight at all here. Probably more like, no, let's do this. Boom. Through that focal point, that's better. It's going to be back like this, and back like this. this. All right, so this is going to turn out probably bad with my drawing. This is why ray diagram just kind of gives you an idea of where that is. You see, it's pretty big. So let's use our data. So let's get some nice numbers here. So let's say the height of this image, the height of the object is 1. Just ignore it. It's 1. 1 centimeter, 1 Mr. Angle, 1 whatever it is. 1 ant length, 1 meter, it's 1. So it's 1 tall. And what's the focal length? We'll call this 10. 10, and now that's 20. So using that equation, 1 over 10 equals 1 over 20 plus 1 over v. I just did it backwards. This is 0.1 equals 0.05 plus 1 over v. Subtract 0.05, 0.05 equals 1 over v. Multiply by v, divide by 0.05, and you get that v is 20. Okay, roughly the same length away from the lens. What's the magnification then? Magnification is negative 20 over 20 or negative 1. So what's the height of the image? If this is positive 1, then its magnification is negative 1. So the height of this image right here is negative 1, whatever, centimeter, meter, whatever. So there's our answer for the first lens. Now we take that data and plug it into the second lens. But instead of calling this the image now, we call it the object. So we're just going to change the image to the object. So the object height is negative 1. Now we plug in some new numbers. What's this distance? This is our image distance. So the focal point is obviously bigger for this lens. So this lens, its focal point, instead of making it 10, let's make it 10, so 10, 20, 30. Let's make it 30. What's this object distance now? This object distance is going to be, well, let's make it like 25. Well, why am I using such hard numbers? I don't know. Let's come up with what the image distance will be then. So 1 over 30 equals 1 over v plus 1 over 25. This one I'll need a calculator for. So 1 over 30, 1 over 30 is 0.033 equals 1 over v plus 1 over 25, which is 0.04. Subtract 0.04 from both sides, so 0.03333 minus 0.04, and then you get negative 0.006667 equals 1 over v, multiply by v, and then divide by 1 divided by that. So 150. Oh, so v is 150 centimeters. So actually, my scale is not even close. Like it's, yeah, these lines, it would have traced it way back to over there. It would have been way over there, 150. So what's my magnification then? Well, using that same equation here, I'm going to replace these. It's negative 150 over 25. So it's 150 divided by 25, which is 6. Or negative 6, I should say. What's the height of my image then? So this is, if this is the height of my object, so if this is, my magnification is negative 6, my height of my image is unknown. The height of my object was negative 1, so it just becomes a positive 6. So positive 6 meters, centimeters. My bad, I screwed up. So I screwed up. This is actually negative 150, and this becomes, so that's negative 150. This is a negative 150, so it makes it a positive 6 for magnification. And that's a positive 6 for the magnification. What's the image height? It's negative 1 times 6, which is negative 6. So let's just use centimeters. Here's what happened. Our object started over here at 1 centimeter tall. The image that it formed became negative 1 centimeter tall, right here, this red one. That went through this lens, and we calculated this image was going to be actually way over here, 150 centimeters away. I just didn't have enough room, and I can't draw straight lines. This right here is actually negative 6 centimeters tall. 6 times bigger than our original image and upside down. So it does work. So the process for actually calculating how, like, multiple things, if I had a third lens, I would just do it I would do it again. If I had a fourth lens, I would do it again. So you just basically, you solve for one lens or mirror, get all your data, then all of your image values, your image distance, your image height, becomes a new object. You just treat that like, ignore everything you just did, get those values, and treat it like a new object. The image distance becomes the object distance for the next problem. The image height becomes the object height for the next problem. And you use those numbers to calculate the next thing. And then you create a new image. And then that new image becomes another object for the third one and the fourth one. I don't think you ever have to do anything more than 2, but because think about any practical thing that uses more than 2 lenses. I can't think of any off the top of my head. So 1 or 2 is all you have to do it for. So great. Hopefully that makes sense. And basically, like I said, the really only tricky one is those diverging lenses because the rays split up, and so you get a negative focal point because the focal point's on our side. Everything else, you just plug in the numbers, what the distances that are given. If you have more than one lens or more than one mirror, you just do it once and then get those numbers, plug it in again for the next one. So there you go. There's imaging the equations. So that's the next step. Boom.